maths from 2022. I'm going to be doing the long questions 2, 3, 4, and 5 in this video, the ones that mathematicians would have to take. So let's get into it. So we've got this expression here, and it's asking us to show that if this is true, then this is true. And okay, so, well, we notice a z squared here there, so we'll square this all up and we'll expand this out. Can't be bothered to work out what 19 squared is, so I'll just leave it like this. Got two cross terms there. And now what I'm going to do is I'm going to add in 4 lots of this term here, only to take them away at the end. So if you see here, I've added 4 lots of this term to this to give it a +2 here, and then I've just taken away those 4 lots here. And the reason I've done that is because now I can sort of re-factorize this. It factorizes into almost exactly the same thing that this did before I expanded out, except there's a plus there. So I can factorize all of this into the same thing I had here with a plus, and then here, this 4 is 2 squared. And then I've got 2 squared x squared y squared, so that's 2xy all squared. And so n here just ends up being 19, and we have our answer. Probably lots of ways you could do that, including just looking at this and expanding and comparing some coefficients with this and stuff when you square this, but, you know, whatever. Find z if x is this and y is this. So put x is 13 and y is 3 into here, and just laboriously work that out. It's -2. Hence, find a pair of whole numbers with this equaling 4. Now, it doesn't seem initially like they've given you much direction with this, because this thing doesn't equal 4, it equals -2. So how do we get something to equal 4? Well, -2 squares to 4, and they've just shown us something to do with squaring, right? And that's when we notice that the reason that they wanted you to do this, look at these two things carefully. This is something squared minus 19 times something else squared equals z. This is something, a bit more complicated, but something squared minus 19 times something else squared. So they've essentially made you write some kind of weird transformed thing to get a slightly different answer here. But that's really helpful, because that means that if I square this, like it said, if this is true for some x, y, and z, and I know it's true for 13, 3, and -2, then this is true for those same values. So I can just put in 13, 3, and -2, but the -2 becomes a 4, and like I said, this thing is of the form something squared minus 19 times something else squared equals that thing. So I just need to work out what these things are, and I get these numbers here, and so 340 and 78 will do that thing. So kind of an interesting question here that we've got going on. And now it says, hence find a pair of positive numbers, whole numbers, such that this is true. And again, it doesn't seem like we've got much direction here, but it says the word hence, so apparently we need to use something that we just did. And we look at this one carefully and we go, well, actually, if I divided that by 4, I'd get a 1. Can I divide these things by 4? Well, because these things are both even here and here, and I'm squaring something even, that means there'll be at least 2 powers of 2 in each of these things. So I can definitely divide this by 4. I can take this is 2 times 170, so it's 2 times 170 all squared, so that's 2 squared times 170 squared. This is 2 times 39, so it's 2 squared times 39 squared, and I can cancel all these 2 squareds, and I'll get this, and so my numbers are 170 and 39, and those would be a pair that do this. Good. Is the solution the only such pair? Well, no, right? Because, and the way that they've asked it, you know, suggests that it's not, because I can do that same trick I did before, because 1 squared is just 1. So I can do this transformed solution here, but because 1 squared is still just 1, if I pop 170 and 39 into here, now I haven't bothered to work out what the hell this is, well, I know the whole thing is obviously 1, but I don't know what I haven't bothered to work out which those numbers are, but the point is I've answered the question. It's not the only pair. Like, whatever this is squared minus 19 times whatever this is squared is 1 squared by this transformation here. So the answer to that is no. Prove that there are no positive whole number solutions to this. Well, what do we notice about this here? Well, 25 is a nice number for this. Like, what we were looking at here was a not nice number, 19. 25 is nice because that just makes this a difference of 2 squares. It's just x minus 5y into x plus 5y. But the problem with this here, whole number solutions, remember, is that we've got something times something equals 1. And the only way to make whole numbers do that is for it either to be 1 times 1 or minus 1 times minus 1. But in either case, you get that y is 0, I think. I think you do, at least. Like, you can just add together these two things, I guess, and you get x is 1 and y is 0 both times, which is not a solution that's possible. So I think not. Cool. though that doesn't seem to make too much sense with this. Oh no, it does. Yeah, it does. Perfect sense. Cool. Yeah, x is 1 and minus 1 and y is 0, but that doesn't match with this. Good. I knew I was doing the right thing when I did it. This is classic maths that they've given you now. It's just a slight change in the question. I think it's the last part of the question. And essentially, they've walked you through very slowly how to do all this stuff. And now they're saying, okay, just do it again with something else. Just do the whole thing again with something else. So, okay, we haven't dealt with this guy at all yet with a 17. So what we do is we go back to the start and say, okay, what's the first thing they asked us to do with this kind of object? Well, they asked us to square it and write it in some other form where you've got some different number squared minus 17 times a different number. And I did this very quickly because I just knew it would be the same thing but with a 17 here, because nothing else about the maths will change. So I just did the same thing but with a 17 here instead of a 19. And now I've got these two things here. But the nice thing about 1, of course, is that 1 squares to 1. So that this seems like it will be helpful. Now, okay, what else do we need? Well, going back to the question, they gave us a thing to start with. They gave us a thing to start with that made something, minus 2, that would square to the thing that they actually wanted. So what I want to do is I want to find a pair of solutions that would not necessarily that make 1, because that's the whole question, but could I find a pair that comes to a number that would square to 1? So previously they gave us 2 options that would make minus 2, which would square to 4, which is what they actually wanted me to do in the next part. So if I can find 2 numbers that make minus 1, I could then square it and find 2 numbers that would make plus 1. So can I find 2 numbers here that make minus 1? And that's a fairly obvious spot. It's 4 squared minus 17 times 1 squared, right? That makes minus 1. And so now if I have these 3 satisfy this, I can plug them into here, and I can do 4, 1, 4, 1, minus 1, and I'll get a pair that make plus 1. It turns out to be this, 33 and 8. So yeah, a really nice question. That was question 2 done. Question number 3 then. So a predominantly graph sketching and integration question, which is good news for me because I like that sort of thing. First thing to notice is that x squared minus 1 is x minus 1 times x plus 1, of course, difference 2 squares, and then I can distribute the n across each of these. And now the reason I've done that is because then when I plug in a 2, I can just see, okay, this is a quartic graph, positive quartic. It's got a double root at 1 and a double root at minus 1, so it's going to look a bit like this. Nice and straightforward. And then I have, sorry, my phone is ringing and I'm not really sure why. I'm going to ignore it, of course. And then I put in 3 instead. And okay, so now I've got a triple root at 1 and a triple root at minus 1. What's that going to look like? Well, I can work out that the y-intercept is at minus 1, right? Because this would expand out to a minus 1. This would be a plus 1. So when I expand that out, I'm going to get a minus 1. It's a positive power 6 x term is the biggest term, isn't it? So it's going to start up here and end up here, a bit like the quartic does. And when it's got a triple root, what happens is that's the point of inflection. So it's going to come down here, inflect through this root, down, inflect through this root as well, and then go back up. And that's very hard to draw into PowerPoint. So I'm just going to get the computer to do it, and it looks a bit like this. Cool. Okay, so, and then it says, actually, I put them on the same axis. So again, I got a computer to do this for me. And it wants all the points that lie on x-axis or y-axis, and the intersections actually lie on both curves. So it wants the intersections as well. So we've got, okay, clearly it's 1, 0. We knew that because of these without the computer's help. And minus 1, 0. We also have 0, minus 1, and 0, 1 as well. So that's cool, that's obvious. Now what about the intersections? Well, we just set this equal to this. And now we can divide by x minus 1 squared and x plus 1 squared because we've already accounted for the intersections at 1 and minus 1, so I can just cancel all those down, expand this out, add the 1, and square root, and we get plus and minus root 2. And now put that plus and minus root 2 into, well, you could put it into these equations, but it'd be easier to put it into this one, right? Because root 2 squared is 2, minus 1 is 1, and then that's the any power is just 1. So this is root 2, 1, and minus root 2, 1 are our 2 other points where the curves meet. Okay, so that's part 1. Without calculating the integral, explain why there's no positive value that this works if n is even. Now, if n is even, that's one of these types of graph that has a positive y-intercept at 1, comes down for its repeated root at 1 here, and then goes back up again, right? If you've got an even power here. Because if you've got an even power here, then you've got an even number of minus 1s multiplying out, so that's going to make plus 1. But that means that the entire graph after 0 in this direction is always above or equal to the x-axis. So that's never going to integrate to 0 because there's no area below the x-axis that could cancel anything out. So the graph is above the x-axis, so this is just not going to ever equal 0 unless you choose a as 0, but we're not allowed to do that, so that's fine. Now, if n is odd, that's going to be different, right? If n is odd, then you're down here to start with, and what you can do is you could maybe put the integral boundary over here, and then you could have this negative area, because of course below the x-axis integrates to negative, and this positive area could cancel, and you'd end up with some a value that between 0 and a would integrate to 0 because of the cancelling out. So that's, I guess I've just explained this, because if you've got an odd number here, you've got an odd number of minus ones multiplying out by each other, so you start down here, and then you've got a positive and negative area to cancel. Just notice as well how this, even if this is odd, the highest power of x is still even, because it's 2 times that odd number, so the graph still always shoots up like this no matter what power you use. It's still going to shoot up like this. So you're definitely going to have this cancelling happen. Good. Find a1. Now a1 is when m is 1, so that's 2 times 1 is 2 minus 1 is 1. So we're just going to integrate this thing to the power 1 between a1 and 0 and hope for that to be 0. So this is not going to be too hard to do. Very mechanical. We just shove them in. We know that if a1 is 0, we get a very trivial solution because we'll be integrating between 0 and 0, which is of course 0. So we can just divide by a1, get this, rearrange, and we'll get root 3. Of course, it's not negative root 3. It could be negative root 3, but they want a positive value. I think it says they want a positive. Yeah, there we are. Good. So it's going to be root 3. Prove that a2 is between root 3 and root 2. So what you can do here is you can just integrate up to root 3 and hope that your total integral is a little bit too positive, and then integrate up to root 2, hope that that's a little bit too negative, and that means that there must be a sign change in between or a 0 in between. A bit like when you first learned like differentiation and you showed that for one x value the gradient was negative and for one it was a bit positive, so therefore there's a turning point in between, that kind of idea. So if we just shove in root 3 and just, again, very mechanically do the integral, it's a bit boring, I won't go through it very carefully. Just be careful when you're doing this kind of thing. So you've got 7 root 3's. Well, they pair up to make 3 each. So there's going to be 6 of them will pair up to make 3 lots of 3, which is 27. And then you'll have 1 root 3 left over, and likewise here, but then you've got a 3 here as well, so that complicates it a bit. Anyway, then you have to sort out the easiest way to show that this is positive. Which I did this kind of thing. This is probably not the best way of doing it, but I think that does eventually show that it's positive clearly enough. And then you just do the same thing with root 2. And you show that root 2 gives you a negative value. Again, try doing it as cleanly as possible, I guess. That's definitely a negative number of root 2's, I guess. And so there must be a 0 in between the two. And so that's what I think I've done. Okay, so without calculating any further integrals, find the approximate value of am when m is very large. So okay, when you send this up to a really big power, what is going to be, what they're asking is, let me just remember what they're asking because I can't remember. Yeah, what they're asking is, for what value do you have to go up to make the integral 0? So when m was 1, you had to go up to root 3. When m was 2, when m was 2, you had to go somewhere between root 2 and root 3. And it's asking, well, what's the limit to that? So it's clearly gone down a little bit from root 3 to somewhere between root 2 and root 3. Now it's saying that apparently if you go up to root 2, you're always less than 0. Just about. And I think the easiest way of explaining what's happening here is by graphing it a little bit. When you send, so this is when m is 3, this case. We drew this earlier. I think it's when m is 2, right? Because this total power was 3. When you make the power 5, it looks a bit like this. So it's a bit flatter towards the middle, which makes a lot of sense because when you take numbers very close to 0 and send them to higher powers, they get even smaller. So there's a longer phase where it's flatter, but then it gets bigger even faster, which we know because the higher you raise the power to, the more it increases a faster rate as you get to bigger numbers. So it increases faster, and it just keeps doing that kind of thing. So I did a few of these. Gets flatter for longer each time, but then starts getting steeper and steeper as you go through. And now the question is, when does it start getting very steep? And we did this earlier, right? We found a really interesting point earlier, much earlier in the question, which was where those two graphs, going backwards quite a long way here, where these two graphs met was root 2, 1. And we think for a second, why did they meet at root 2, 1? And the answer is because, of course, if you substitute root 2 into here, no matter what the power is, root 2 squared is 2, minus 1 is 1, and 1 to the power of anything is 1. So all of these graphs that I was sketching here always go through 1. I'm just flicking through all the working that I did earlier, always go through root 2, 1, and then accelerate very, very fast, because then you're suddenly, as soon as you pass root 2 by even a little way, you suddenly start raising something even just slightly bigger than 1 to a very high power, which is going to eventually get to a very big number. And so, because you accelerate rapidly after this root 2 point, if you just send them up far enough to the point where it accelerates incredibly rapidly, any area that you take out of that will then start cancelling with this relatively puny area next to it. Because as soon as you pass sort of root 2, you start getting very, very fast or large increases in area, because this line basically starts becoming vertical. And so any tiny shift past root 2 gives you a huge amount of area in total extra. And so the limit of this is root 2. Even though this seems like it's weird, that's what a limit means. Is it wouldn't actually be root 2, but the limit it tends to is root 2. Is what you need to say. Cool, I hope I explained that okay. We're actually somehow only halfway through this because we've got 4 questions to do, and we've done 2 of them. Anyway, sketch this graph here. Now, well, I know that root x looks kind of like this, and I know minus x over 4 is a line going downwards. The thing is, when x is very big, this is going to be the only term that matters. It's a bit like an x and an x squared term. The x squared massively beats out the x term. So as x gets really big, this graph here is just going to tend towards being whatever this is. So what's going to happen is the graph is going to go, and likewise for small values of x, when you root a very small value between 0 and 1, the thing actually gets bigger. So when you've got very small inputs between 0 and 1, this is going to be the much more important term. So the graph is going to look a bit like it was just this graph, so it's going to go up like this. And then when you get bigger values of x, it's just going to start looking like this graph, which is just a line downwards. So it looks a bit like this. And of course, it doesn't exist over here because you can't put a negative input into this part. So we're going to get a graph that looks a bit like this. Find the coordinates turning point, where we can just differentiate if we want to, and then solve it for 0. That was not too difficult. And we get the point 4, and then when we substitute in 4, we get the y value of 3. Good. Okay, now if I call that function f of x, look at this graph here. It looks pretty similar. Actually, all it is f of 4x plus 1, I think, nearly. Like, if f of x is this, f of 4x plus 1, replace this x with 4x plus 1, and this one too. Sort this out a little bit. This is just 4x over 4, which is just minus x. And this is a quarter, which is then minus a quarter. So it's not quite this graph, because the one they want me to deal with is minus 1. So all I need to do is add another, I think, 3/4. Sorry, take away another 3/4 from this. If I take away 3/4 from that, I get to minus 1. And so this is the transformation I need to do from my original graph. And to do this, you do BIDMAS sort of in reverse order. So you start by shifting the graph 1 to the left. Yeah, that shifts it 1 to the left, doesn't it? Then you compress it 4 times horizontally. Then you shift it down 3/4. So we shift this 1 to the left, which takes it to 3, 1. We then compress it factor 4 horizontally, which makes that 3/4. Again, that doesn't change, so it's 3/4, 1. And then we move 3/4 down from here to get 3/4, a quarter. Don't ask me why we do it in this order, because I honestly don't know. Point A is at 1, 0, point B is at, sorry, minus 1, 0, point B is at 1, 0. Okay, cool. Curve C is defined to be all the points that satisfy the distance from A to P times the distance from B to P is 1. Okay. So can we find an obvious point that would exist here? Well, 0, right? Because the distance there is 1, the distance there is 1, and then 1 times 1 is 1. So that's a very obvious point. But there are probably going to be others, right? Because, for example, 2 times a half is 1. And it seems likely I could draw a line sort of this way until this distance is 2, and make it such that that distance is a half. It seems like I could do that. So there's probably another point up here somewhere. First, though, it wants me to find all the points that lie on the x-axis that do this. So, okay, I've got to think, are there any more on the x-axis here? Well, initially I didn't really think there were, but then I thought, okay, let's just pick a point and call it x1 and actually do the maths. So the distance from this point to B is just x1 minus 1. And what the mod function literally means is the distance from one thing to another. That's why they've used it here as well. So the distance from x to 1, and again, the reason I put it in the mods is because if it was here, the mod would still work out that distance for me, which is good. I don't want it to be negative because that will mess it up. And likewise, the distance from x1 to this is x1 minus 1, or just x1 plus 1. as well, and again in the mod root function for the same reason. Now I can just expand this out, I can put the mods together, and I get this. And now this means that x1 squared minus 1 is either plus 1 or minus 1, because of course if it was minus 1, the mods would just make it 1, so that's fine. Add about 1 to both sides, square root for x is plus or minus root 2. So at root 2, this works apparently. And that actually makes sense, because root 2 minus 1 times root 2 plus 1, if you do some maths, everything sort of cancels and you get 1, which is nice. And here x1 becomes 0, which is the one I already knew. So there are 2 points here that work. The other one I didn't bother to put down apparently. But there's definitely 3 points on the x-axis that do this, and I've got them there. Finds an equation in the form f of y equals f of x that will do this, explicitly determine f of x. Okay, in this region here, x greater than 0, y greater than 0. Okay, so I'm looking for points, and again, I mentioned the one that seems likely to be about 2 away from here and a half away from here as a candidate point. Let's just call it x, y. And now let's do this same thing that I did here, but in 2 dimensions. So the distance from this point to down here, well, in terms of x, it's x plus 1, right? This distance here is x to this coordinate, and then there's 1. So it's x plus 1. This distance is y, because that's just what this means. So x plus 1 squared plus y squared is this distance squared. So I can write that like this. So that's the distance from here to here. Root, of course, because that's how Pythagoras works. The other one I can write as x minus 1, or 1 minus x. It doesn't really matter, because when you're squaring it, those two things are the same. And again, plus y squared. And again, take the root of that and then multiply those two distances together and we get 1. Now, of course, we can put these roots under the same thing if we want to. Actually, I think I just squared both sides here because 1 conveniently squares to 1. And now I can start multiplying these things together and I get this. Now, this is a formula or a function in terms of x and y for this graph, but it says explicitly determine. And in case you don't know what that means you need to write it in the form y equals stuff with x's. So that's a little bit annoying, but I need to convert this into something that says y equals. Now, how on earth do you do that? Well, I'm just going to rewrite it like this for a second. So I've collected the y squared bits together. Here, I've put all the stuff that doesn't have any y's here, and then the y to the 4 over there. Now, if I just expand and simplify this and this a little bit, this is very mechanical, I won't go through it too carefully. You get this eventually, this eventually, this eventually. Okay, cool, so we're finally at something that looks a bit more simple. And now this is a quadratic in terms of y squared, right? Here's y squared all squared, here's y squared, and I've got some coefficients and one more thing that doesn't have any y's in it. So this is just a quadratic in y, or in y squared I should say, which means I can use the quadratic formula on it in terms of y squared. So my a coefficient is 1, b is this, c is this, and I can say from the formula, because this quadratic is built out of y squareds, y squared squared and then y squared there, I can say y squared equals the stuff in the formula, which is all of this when you put it in. Again, do some very mechanical maths here. You're just expanding things out and cancelling things down. You can take a 4 out of this, which helps you massively, because it's root 4 times root this, and then root 4 is 2, and then all these 2's can cancel, which is quite nice. And you get this here, and then that's y squared, and so we can root the whole thing to get y is that thing there. Now the thing is, y has to be positive, because we're in this region. So minus, 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 I mean, you can't even take the root of that, so this must be a plus to have any hope. And because y is positive, I don't need the plus or minus, I know it must be the positive one. So I think y must be this. And just take a moment to realize, and this is quite a hard spot, but remember part 1 and 2 that we did much earlier? Look at this thing here. That's vaguely like this thing here. Maybe even more so if I swap this term with the negatives and make this. And now we can see it's actually exactly the same, except there's an extra square root all the way over the whole thing, and the x's have turned into x squareds. Aside from that, it's the same, which lets you know that you're basically done the right thing here. Like you're doing pretty well because you've made something that is very similar to what they were talking about before. Last 2 parts here is to use part 2 to determine the coordinates of the turning point of this. So okay, how are we going to use part 2 to do that? Well, we know the turning points of this, we worked that out. So how do we change that to be the turning points of this? Well, there's a couple of things to do here. Firstly, y is the root of all of this. So whatever x was to get the turning point, we're going to, and whatever output for y that gave us, we're going to root that to get our new y coordinate. So we just need to root a quarter, which gives us a half. And now for what x value do we need to put in? Well, when we put in x is 3/4, we got a turning point here. But if we're going to square the x before we do the computation, that means we're going to need to put in whatever the square root of x was, or whatever the square root of this is, to get the same thing. So the square root of this is root 3 over 2. And so if we put root 3 over 2 into this, we square it out and we do the same computation as this, but then we square root at the very end, and when we square root a quarter, we'll get a half, and so this will be our new turning point. Notice as well, actually, that again, that's in this range, but because these x's are all squareds, you could also use the negative of this, because you'd square it out anyway, and so there must also be a turning point in negative root 3 over 2. Now that's not relevant to part 5 because of this bit, but it's interesting and very relevant to part 6. Now, in number 6, you need to remember what the question is actually about. Remember the question was about 2 points at -1 and 1, and we're sketching all the points that make this whole distance times distance equals one thing. And we already found the distance point here, we already found a point at root 2 and minus root 2, which are these two things that I've put there. We've already found a turning point here. I just mentioned how a turning point at minus root 3 over 2 and a half also exists. And it's pretty clear that we're going to sort of come up here and come down again, like this, I think. But the thing is, again, think about it in terms of distance from this whole distance idea. If it does this on this side, it must also do the same thing on the other side. Because we're just talking about distances from A to B. That must be symmetrical. And likewise, it must be symmetrical over this side as well. So we end up just drawing some kind of loop shape like this. And again, PowerPoint is very difficult to draw curves in, so maybe your curve should be better than that. But it looks a bit like this, and that's kind of our general idea. Yeah, this should be at the turning point and stuff, but I really couldn't be bothered at this point to make this proper. And partly because I had looked at this question in advance, and I was like, oh my god, what is this? It's huge. Okay, so this is a really nice little trick on if you haven't seen the Monty Hall problem, I'd highly suggest that you look up the Monty Hall problem. As soon as I started reading this, I thought it was going to be that. It turns out that it's not, but it's a nice little change on it. So she's in a TV show. There are n items behind n doors. She picks a door, and the item is revealed. Now, any item that's revealed, she wins. Any item that she sees. Now, so she sees an item, the door is shut, and the host gets to choose whether to swap it with the item behind the door to the left or the right of the one that she picked. Right. And then she picks again, and she sees a new item, and she wins that item, and it keeps going until the number of rounds that is determined by the host ends. Right. And she wins all the items that are revealed. Now, there's only one change to this, which is that if she picks a door on the edge, like door number 1, the host can only flip it with door number 2. Right. The doors don't go in line like a circle or anything like that. If she picks door number 1, the items behind 1 and 2 must swap with each other. There's no choice. The host can't choose which one to do, left or right, because there's nothing to the left of door number 1. And likewise with the door at the end, whatever the last door is, has to be swapped with the door before it. That's the only sort of trick here, and we're of course going to use that to our advantage because it's good for us to know exactly what the host can do, and there's only one situation where the host can do one thing. So okay, so let's draw out these 13 doors then, because they're saying n 13 doors to start with, and apparently Alice has 7 choices to make this first time, and she wants to get 7 items. Is there a way to guarantee 7 items? So okay, let's just pick door number 1, and she wins the item behind 1. The host then has to swap these 2 over, that's fine. And now, because we could pick this door because then we guarantee item number 2, but we know there's a 3, we know item 3 is here. I've called the items 1, 2, 3, 4, by the way. We know item 3 is here, so we may as well pick it and get item number 3. Now, it doesn't matter what he swaps here, the host, because my plan is just to pick door number 5, which can't have been swapped here. It's too far away. So just pick door number 5, get item number 5, and then just keep going, pick door number 7, and then 9, and then 11, and 13. And that's 7 choices, I believe. That's 7 doors, 7 items, and so we can win 7 items every single time. It really didn't matter what the swaps were, because we were picking too far away from where the swaps took place. Okay, and likewise here, if you're picking an odd number of doors, and you only have to have k plus 1 choices, you can just pick all the odd numbers. This is a fancy way of saying that, I guess, until the end. Good. What about a slightly more efficient thing? So n is 13 again. Can we find a way to do 10 choices and get 10 items? So we have to be much more intelligent here. So let's pick door number 1 and get item number 1. And now he has to swap 1 and 2. But now, of course, that means we can pick door number 1 again and guarantee ourselves number 2. And then he has to swap them back. So we've basically got 2 items for free here. The doors are everything is as they were. We know everything's as they were, and we've got both of these items. Good. So now let's go to the other end and do the same thing. Right? We pick 13. He has to swap that with 12. Then we pick 13 again, and we get item number 12. So this is our system: door 1, 1, then 13, 13, and we get 4 free items, and the situation is exactly as it was at the start. So okay, how do we continue in a better way? Because we can no longer force the host to do anything, because we don't want to pick the door on the end again because we've already got item number 1. So we have to pick these things in the middle. Now what we can do is we can pick door number 4 here to get item number 4. And what we can say is, no matter what the swap that's done here, whether the 3 is swapped or the 5 is swapped with number 4, we can just pick that door again and get either item 3 or 5, whichever one he swapped it with. And it really doesn't matter which. Because then what our plan is, after he's done a swap again, is to move on to the next triplet which can't have been affected by any of our swaps, and pick the middle one from there. And do exactly the same trick. Pick it, he swaps it, pick it again, because that guarantees you either 6 or 8, whichever one went into that slot, and do it again. And then likewise, there's one more triplet left, which we can do exactly the same trick on. So pick door number 10 twice more, and we get 10 choices, I think. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And everything is guaranteed. And this is just saying, express your strategy properly. And I think I just did that out loud, but something like this would work well. Picking doors of the form 3i plus 1. Again, you didn't need to pick the 13s first. You could have gone 1, 1, 4, 4, 7, 7, 10, 10, 13, 13. So picking doors of this form, I guess, starting with I as 0 until the end, picking them twice. So 1, 1, 4, 4, 7, 7, and so on. For n equals 3, so this is going to be a nice one because it's very small. Can we guarantee all 3 items? Of course we can. We can pick door number 1. He has to swap 1 and 2 over, so pick door number 1 again to get item 2. 3 has been left alone this whole time. After the swap back again, pick door number 3. Easy. With 5 doors, pick door number 1, then pick door number 1 again, because these two would have swapped and then swap back, you get 1 and 2. Pick door number 5, pick door number 5 again, because these two swap, you get both 2 items. 3 has been left alone the whole time, so then you pick door number 3. Easy. Now this one is the one that really requires some thought. For n is 13, which is the previous case we saw, and we found a sequence of 10 doors, now we have to find a sequence of 11. And this one threw me for a long time, because it felt like what we did before was optimal, but there is an even smarter strategy you can use. You do the same thing to start with. You pick door number 1 twice to get these 2 prizes. We've seen this before. And you can also pick door number 13 twice to get those 2 prizes, right? Because they just swap and you pick them both and you get it. Now, previously we chose that triplet, and that triplet, and got 2 out of every 3, which got us 10. But there's a slightly smarter strategy you can use, which is you completely skip number 3, and you pick this triplet here. And you pick door number 5 twice to get 2 of these 3 items. So door number 5, doesn't matter what the swap is, door number 5 again to get the other one, and you get 2 out of those 3. Then you skip door number 7 and get 2 out of these 3. So pick door number 9 twice and get 2 out of these 3. And now what you've done is you've got both of those items, you've got 2 out of those 3 and 2 out of those 3. And 3, 7, and 11 cannot have moved, because you've only picked this door, which doesn't move the 3, this door, which can't move the 3 or the 7, this door, which can't move these 2, and this door. So now you can just freely pick door 3, 7, 11. It doesn't matter what the swaps have done after that, because they're too far away from each other, and you get items 3, 7, 11 for free. And that's 11 items. And here you just need to kind of write that in a fancy way that picks you up the last marks. And finally, for n is 6, is there any sequence that can get all 6 items? And the problem here is you pick up, the way that they phrased it suggests no, right? You pick door number 1 twice, obviously, and door number 6 twice to get all 4 of these ones here. But then your problem is, when you pick, say, door number 3, obviously you don't want to pick either of these doors because you'll get the same prize twice, and you can't have that. So you pick door number 3, say, but then you don't know whether 2 is going to go into there or 4 is going to go into there. So let's just say we've picked door number 3. You don't know whether you're going to see this or this. And so to get prize number 4, you don't know whether to pick door number 4 or door number 3. And so there's no way of getting this to work at all. Now, I thought about some other fancy strategies that require remembering which prize went where and whether there was any way of doing that. I couldn't quite find a way to do it, though I couldn't really figure out whether it was impossible. But in either case, I think the wording of the original question sort of suggests that you can't be intelligent. It wants a list of doors beforehand without actually seeing the prize that you're getting. It doesn't want you to make it up as you go along and be smart about it and pick doors based on what you've got before. It wants a string of doors before you even start. So no matter how the swaps are performed, so not being able to see and adjust as you go along, it wants a sequence that guarantees it anyway. So even if you were going to be smart about this, I was thinking about like picking door number 2 and then remembering which door had swapped into there so that you could remember and track the items as they went along. But I don't think that's what this question is allowing you to do. I think it just wants a string of doors that beforehand you can just know you're going to pick and just completely ignore what prizes you're getting and just win anyway. So anyway, yeah, that was quite a nice question. An interesting spin on the Monty Hall problem. Thank you for watching, and I'll see you next time.